Okay, so let me see. Yeah, I have a couple of announcements. For me, there are three types of students in this class. There are those who are registered, those who are auditors in person, and those who are auditors online, okay? Only registered students and auditors in person have access to the National Taiwan University Cool course site, okay? And so every day when you come, you have to sign the attendance sheet. So that way I would know that you are an in-person auditor. Or you are registered. If you are registered, you'll be in the pool course site, for the whole semester. But if you are an in-person auditor, you have to keep coming in order to remain an in-person auditor. Okay, so if you miss, like 2 lectures, you will be deleted from the Cool course website. Okay, now if you have a good reason to miss classes, then you should talk to me about it so that you can remain, on the Cool course website. Now, for the online auditors, I will post some course material on my personal website. And I'll put my personal website here. So, so I have already put a file there. It's a review of manifolds. It's only 13 pages, okay? And so everybody should read that. Yeah. And the lectures are being recorded, and the video recordings are posted on YouTube so that everybody has access to it. Now, I'm afraid that this might be an incentive for some of you not to come to class in person because you feel that you can just watch the video, and that's why, I'm gonna check the attendance sheet every day, okay? To see whether you are coming to class. I mean, there are many advantages to coming to class in person because, you and I can interact, and I encourage you to speak English. It will improve your English, and I get to know you, which is good for you. And sometimes I might give presents to people who come to class, okay? Yeah, so yeah, maybe I'll give you some present next time or maybe next week. Yeah. I won't tell you what they are, you have to come to class. Yeah, I watched the videos and I realized that my posture is terrible. So I have to watch my posture. Okay, are there any questions? Oh yes, some students says you don't have access to the homework? Really? Just a minute, your homework is on Grayscope. Did you go to Grayscope? I think if you have access to the NTU Cool site, you should be able to go to Grayscope and see your homework there. you know, because your homework will be submitted through Grayscope. No? Oh, so nobody can access Grayscope?
There was the say it's just
Well, originally I put the homework under assignment, okay? But then I later thought that I should put it under Grayscope because that's where you'll be submitting the homework. And I, you know, enter all of your names in Grayscope. Okay, we'll try to fix it later, okay? And I can always put it back under assignment, yeah. All right, any other questions? Okay, so today is lecture 3, and I'm going to talk about diffeomorphism invariance. You know, and I should also have time to talk about long exact sequence, the long exact sequence in cohomology. Yeah. Okay, I'm going to assume that you know what a C infinity map is between manifolds, okay? If you don't, you know, you can read the book or you can read the summary of manifolds. But basically, you know, a C infinity map, if you, yeah. I want to talk about the pullback under a C infinity map. Okay. Yeah, so, you know, like if you have a map between manifolds, say from N to M, and you want to know if it's C infinity at a point P in N, then what you do is you take a chart here, phi, okay? So it goes to an Euclidean space Rn. And you take a chart here. And it also goes to some Euclidean space M. This should be psi. Yeah, now let's move that board up. And so you can go backwards here by inverse, and then you look at the composition, psi composed with F composed with phi inverse. And now that's a map from Rn to Rm, okay? So, so the definition is that F is C infinity at P if, when you look at this map from Rn to Rm, psi of F of phi inverse is C infinity at phi of G. Okay? Yeah, so that's the definition of a C infinity map. You just look at the expression of F in local coordinates, and when it's a map from Rn to Rm, you know what it means to be C infinity. Yeah, it's infinitely differentiable. All right, so suppose we have a C infinity map, and we have a differential form here on M, okay? So I want to define what it means to pull it back to N. So the pullback F star, okay, from K forms on M to K forms on N, it's defined so that it has certain properties. Okay. One, that when omega is a zero form, so it's just a function, okay? So let's say it's just a zero form. It's a function. Then the pullback is just the composition, follow the arrow. So the pullback of G is just G composed with F. Okay? Makes a lot of sense. Huh? So if this is G, the pullback, it's just the map G composed with F. Okay? And then for forms, okay, you want the pullback to to commute with everything. Okay, so the pullback commutes with addition, scalar multiplication, the wedge product, and the exterior derivative. Okay? So what does that mean? So, that means, for example, the pullback of the sum is the sum of the pullback and so on. The pullback of D of something is D of the pullback. Okay. And yeah. And then if you have two maps and you take the composition, the pullback reverses the order. Okay? If you just think about function, that makes sense because if you have F from N to M and G from M to P, and you have a function G, okay, then you see that, F composed with G pullback of little g is going to be G composed with sorry, the way I have written it, this should be, G composed with F. Yeah, so G composed with F of G should be G composed with G composed with F. And then, then that is F composed with G composed with G. And I'm running out of space, so I'm gonna write it on this blackboard. Mhm. And that's F composed with G composed with G. Okay? Yeah. So pullback reverses the order of composition. Okay? In the language of categories and functors, it says that this pullback is a contravariant functor. Okay? It just means that you reverse the order of the maps. Okay? Now, if you want those properties, then, you know, like, what is the formula for the pullback? So if, you know, omega is a K form on M, then on a chart, say U, Y1, let me see, I think I'll call it V, Y1 to Yn of M. You know that omega it can be written as a linear combination of dyi1 wedge dot 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 dyik, and then the coefficients depends on I1 and IK. And we have a shorthand for this, AI dyi. And so the pullback, because it commutes with sum and scalar product and wedge product and D, so it should be, you know, the pullback of AI, and then it commutes with D, so it goes to the other side, the pullback of YII, which dot 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 D F star of YIK, and then this is the sum of AI composed with F, okay, and the pullback of YI1 is just YI1 composed with F. Okay, now YI1 composed with F is the I1th component of F. So, you know, we can write it as AI composed with F, the FI1, which dot 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 the FIK. And this just means the ikth component of F, okay? And so, in fact, so we can take this to be the definition. If you have a form, you write it locally in terms of coordinates, and then you define the pullback to be given by this formula on, on some, you know, like on some chart in N. Okay? And this formula, well, depends on the coordinates, but you know, you can show that it's actually independent of the coordinates, so it's well defined. Okay, yeah. But usually, when you do calculations with the pullback, you do it locally. So this is the formula you use. Right? And yeah, so the pullback has these properties if you define it this way. Okay. Now, let me move this down. Okay. Okay, now I want to show that the pullback of forms induces a pullback in cohomology. Okay. So let's see. And I'll need this. Yeah. All right, so pullback in cohomology. And it's because of this property, the pullback commutes with D. Okay? Because of that property, F star takes closed forms to closed forms. And exact forms to exact forms. Okay. All right, so let's see if you remember the terminology. What is a closed form? What's a closed form? A closed form is supposed to be a cocycle. What's the definition of a closed form? Yeah. No, come on. Are you too shy or have you really forgotten? Oh, good. Yeah, a form whose exterior derivative is zero. Right. Very good. So suppose you have a closed form. So that means d omega is zero. So omega is a closed form. Okay, that means d omega is zero. And so let's look at d of the pullback of omega, but the pullback commutes with d, so this is f star d omega, and that's f star of zero, so that's zero, okay? So that says that f star omega is closed. Let's go to this side. Yeah, so f star of omega. Right? So the pullback takes a closed form to a closed form. And now what about an exact form? What is the definition of an exact form? Yeah, very good. So an exact form is D of something. Okay, so let's say you have an exact form, D tall. That's exact. And if you pull it back again, D and F star commute. So the pullback of an exact form is D of something. So it is exact. Okay? Yeah. All right. That means the pullback actually goes from the closed K forms to the closed K forms. From ZKM to ZKN. Yeah, and it takes the exact forms to the exact forms. Okay? You know, you can compose this with the quotient, compose it with the projection to the quotient, which is in the cohomology. Okay. So you have a map, F star, that goes from the closed forms all the way to cohomology, and the exact forms goes into the exact form. So this is going to go to 0. The exact forms will be in the kernel, and so that means you get an induced map, right? Thus. Okay. Thus, there's an induced map. An induced map from ZKM over BKM to ZKN over BKN. I call the induced map F sharp or FH, F hatch. And this is the cohomology of M. This is the cohomology of N. And so F hatch, it takes a cohomology class to the cohomology class of the pullback. That's the inducement, okay? So it's basically the same as F star, except it's on cohomology classes. And it's going to satisfy the same properties as F star, okay? So, well, if you have the identity on a manifold M and you take the induced map, okay, that is going to be given by the class of the identity, the pullback by the identity. The pullback by the identity doesn't change anything. So you're going to end up with the identity map on the cohomology of M. Okay? And then if you have a composition, and then you take the pullback, you're going to get G hatch composed with F hatch. Okay? These two properties are called the functorial properties. Mhm. Yeah. Okay, now usually we use the same notation for the induced map as for the map on forms. So usually instead of F hatch, we just write F star. Say, that's just notation. So usually we write F star for F hatch. Okay? So F star can be a map on forms, or it can be a map on cohomology classes. Okay, yeah. So I want to now show that cohomology is a diffeomorphism invariant. That means if you have a diffeomorphism of manifolds, their cohomology should be isomorphic. Okay, yeah. What is a diffeomorphism? I haven't defined it, but what do you think it should be? You know, like an isomorphism of vector spaces is a linear map that has an inverse, which is also a linear map. Okay, so what should the definition of a diffeomorphism be? A diffeomorphism, yeah, so it's a C infinity map that has an inverse that's also C infinity, right? So F from N to M is a diffeomorphism if there exists a map G going the other way, and okay, it should be C infinity. So there exists a C infinity map, G going the other way, such that when you compose them, F composed with G should be the identity on M, and G composed with F should be the identity on N. Okay, so that's a diffeomorphism. And so the theorem is that a diffeomorphism of manifolds induces an isomorphism in cohomology. And that means whenever you have two manifolds that are diffeomorphic, they should have the same cohomology up to isomorphism. Okay. So theorem. Diffeomorphism induces an isomorphism, a vector space isomorphism in cohomology. Okay. And it's really easy because it's a diffeomorphism, so it's got an inverse map. And then you can just take the star of both sides. Okay. And you know that the star of the composition is the composition of the star, but in reverse order. And the star of the identity is the identity on cohomology. Okay? And then if you do the same thing to G composed with F, that's the identity on N star, and you get the same thing, right? F star composed with G star is equal to the identity on the cohomology of N. And that shows that F star and G stars are isomorphisms, okay? Yeah. Okay. So that means the Ram cohomology is diffeomorphism invariant. So if you have two diffeomorphic manifolds, they have isomorphic de Rham cohomology. Let's consider an interval, okay? So to make it easy, I will consider the interval, say from minus pi over 2 to pi over 2. So this interval is diffeomorphic to the real line. And what is a map that gives you the diffeomorphism? Can somebody tell me a map? Oh yeah, the tangent, right? Because the tangent has a graph that looks like this. Oh no, I shouldn't use green. Green on green is not readable. Okay. So the tangent has a graph that looks like this. It's 1-to-1 and onto, and it's infinitely differentiable. And its inverse is arctangent. Okay? So the tangent is a diffeomorphism. And that means it induces an isomorphism in cohomology. So the tangent star from the cohomology of R to the cohomology of the interval is a vector space isomorphism. And we already calculated the cohomology of R. So now we have the cohomology of this interval. Okay, and what's the cohomology of R? Let's see if you remember. I'm sure you know it. You just don't want to tell me. The cohomology R, we calculated it last time. Yeah, it's 0 in degrees greater than 1. It's R in degree 0 and 0 in degree greater than 0. Okay, and in degree 0, right, it's represented by a function. So which functions represent the cohomology in degree 0? The constant functions. Okay? There's nothing special about this particular open interval because any two open intervals are diffeomorphic, right? So we have calculated the cohomology of an open interval. So yeah. Any open interval AB is diffeomorphic to minus pi over 2 to pi over 2 because, well, let's say this is minus pi over 2 to pi over 2. And then you have A here and B here. Then you see this, okay, you can just draw a straight line like this. So that would be the graph of a function from minus pi over 2 to AB. It's going to be a linear function, so it's infinitely differentiable. Okay, so this is the graph of linear, the graph of a linear diffeomorphism from minus pi over 2 to AB. And this means that you now have the cohomology of any open interval. It's R in degree 0 and 0 in degree greater than 0. Okay? Yeah. Okay. Okay. Now, what about compact supports? If you have a function with compact support and you pull it back, does it still have compact support? Okay, it's a yes or no question, all right? I'm going to take a poll. How many people say yes? The pullback of a function with compact support has compact support. Raise your hand. Okay, and how many people say no? The pullback of a function with compact support does not necessarily have compact support. Raise your hand. 1, 2, 3, 4, 5. Oh, okay. Yeah, more and more people are raising their hands. Good, very good. Uh-huh. Yeah. Yeah. So for compact support, you don't have a pullback on forms. Okay, and it's easy to get an example. So the pullback okay, of a form with compact support need not have compact support. However, if it's a diffeomorphism, then of course it still has compact support. Because diffeomorphism is bijection, so there's really no difference between the pullback and the function, you know, where it's not zero. At one point, it's not zero, like at the corresponding point, yeah. But if F is a diffeomorphism, then F star takes a form with compact support to a form with compact support. Okay, so if you only work with diffeomorphisms, everything goes through, and therefore, cohomology with compact support is also a diffeomorphism. Okay, so for diffeomorphisms, everything goes through as before. So the cohomology with compact support is also a diffeomorphism invariant. And this means that we also know the cohomology with compact support of any open interval. Okay, okay, let's take a break for 10 minutes. And I want to remind you that everybody who comes here in person has to sign the attendance sheet, okay? So that I know you are attending, and so that I will keep you on the website, okay? If you miss 2 lectures, you will be deleted from the NTU Cool website, all right? Okay, yeah, see you in 10 minutes. Yeah, all right. I want to encourage you to speak in class. You know, you can ask questions, you can answer my questions. I noticed that many of you are reluctant to speak when I'm sure you know the answer. So if it's because you don't feel comfortable speaking in English, you know, you are welcome to speak in Mandarin. Yeah. But I'll try to speak in English with you, you know, because it's good for you to get some exposure and some practice in English. All right. Okay. So the second part of the lecture today is on exact sequences. And this really has nothing to do with differential forms of manifolds. You know, this is what's usually called homological algebra. But since I don't assume that, so I will go through the basics, okay? So we start with exact sequences of vector spaces. So a sequence of vector spaces, say Vk to Vk plus 1, coming from Vk minus 1, with maps Fk minus 1, Fk, and so on, is exact at Vk if the kernel of Fk is the image of the preceding map, Fk minus 1. Okay? And this sequence, the entire sequence is exact if it is exact at Vk for all k. Okay? Okay? And k can go from minus infinity to infinity. Usually will start at 0, but in principle, it can go from minus infinity to infinity. Okay, so that's an exact sequence. And then a short exact sequence is when you have only 3 terms. A sequence. How to put it? A short exact sequence is an exact sequence of the form 0 goes to A, goes to B, goes to C, goes to 0. So it's got only 3 non-zero terms. And now let's just see what exactness at A means. If it's exact at A, that means the kernel of I is the image of the preceding map, but the preceding map is 0, so the kernel is 0. What is a linear map whose kernel is 0? What can you say about a linear map whose kernel is 0? It's injective, okay? So I is injective. Okay. That's from linear algebra. So exactness at A means that the map coming out from A is injective, and then exact as C means that the image of J is equal to the kernel of the map coming out of C, so it's the kernel of 0. Yeah, so just a minute. Oh yeah, right. And what is the kernel of this map? The kernel are the things that go to 0. So what's the kernel of the 0 map? It's a whole space C. Okay, so that says the image of J is the whole space, and that means J is surjective. Okay? So when you have a short exact sequence, you know right away that I is injective and J is surjective. Mm-hmm. And exactness at B, well, that's just the definition. it means that the image of I is the kernel of J. Okay. Okay. Yeah, so we have this theorem that if you have a short exact sequence, Ij, that's equivalent to, okay, the first map is injective, J is surjective, and B over A, because A is really a subspace of B, is isomorphic to C. Okay? That's what a short exact sequence means. Okay? Yeah, I'm not going to prove this. You know, it's just simple linear algebra. Okay, so that's exact sequences of vector spaces. And now I want to talk about exact sequences of Cochain complexes. Yeah. Okay, so first of all, what is a cochain complex? It's a generalization of the de Rham complex. So a cochain complex, also called a differential complex, okay, is a sequence of vector spaces and linear maps I denote it by a script C. So CK minus 1 going to CK, going to CK plus 1. And the maps I call DK minus 1 and DK here. So it's a sequence of vector spaces, but it's not assumed to be exact. You just assume that the composition of two adjacent Ds is 0 for all K, okay, in Z. That's a Cochain complex, okay? Now, because the composition of two Ds is 0, the image of dk minus 1 will be in the kernel of dk, okay? So, so you can define, whenever you have a Cochain complex, you can define its cohomology. Yeah, so this condition that d squared is 0 implies that the image of dk minus 1 is contained in the kernel of dk. So therefore, you can take the quotient and that's the cohomology of the Cochain complex. Okay? And an example is the de Rham complex, where you have differential forms. They satisfy d squared equal to 0, and then the cohomology of the de Rham complex is de Rham cohomology. Okay, and well, that, in mathematics, whenever you define an object, you have to define what right away. Like if you define groups, then you have to define what? Group homomorphisms, right? And after you define vector spaces, you have to define linear maps. After you define manifolds, you have to define C infinity maps. After you define topological spaces, you have to define what? Continuous maps, okay? So after you define Cochain complexes, you have to define Cochain maps. Yeah. All right, so let's define what a Cochain map is. So a Cochain map should go from a Cochain complex to another Cochain complex. So suppose you have two Cochain complexes. So one you call A, okay, and the other you call B. Okay. Yeah, I'm going to omit the subscripts on the D's because, it looks too messy otherwise. Oh, maybe I shouldn't. Let's put dk there and dk prime here, okay? This should be dk minus 1, dk minus 1 prime. So a Cochain map from A to B is just a sequence of linear maps, one for each k, okay? So let's call it phi k minus 1, phi k, phi k plus 1. It's a sequence of linear maps so that this diagram is commutative, okay? Okay, so that's a definition. A Cochain map from phi from A to B is a collection phi k of linear maps okay, for all k, such that this diagram should be commutative. So you can just look at one square. So that means phi k plus 1 composed with dk. This side should be equal to this side is equal to dk prime composed with phi k, okay, for all k. That's a Cochain map. Now it looks like the property of the pullback, right? It looks like phi commutes with d. And so if you have a Cochain map, because of this property, is going to take cocycles to cocycles and coboundary to coboundary. So I should define that, okay? So zk of C, I should have defined that earlier. It's, you know, the set of all C in CK such that D of C is 0, and BK of C is the set of C in CK such that C is equal D C prime for some C prime of degree 1 less, so it's in CK minus 1. Okay, so it's just the same type of definition as for closed forms and exact forms. Okay? Yeah. Okay. And so just like for the pullback, a Cochain map or induce a map in cohomology. Let's see. Okay. So a Cochain map B from A to B induces a linear map B star in cohomology. Okay. And now I have defined a Cochain map between two Cochain complexes. Okay. So a short exact sequence of Cochain complexes, say 0 from A from B, C, um, where A and B are Cochain maps. Oh, sorry, I and J are Cochain maps. Is a sequence of is a sequence of oh yeah, so well I and J are Cochain maps, so that means for each K, you know, you have IK and JK, right? So let me see. Oh gosh, so this should be up there because I'm going to write on this side. I seem to spend a lot of time just manipulating the blackboard, you know, but maybe that's good for you because you get some time to relax. Yeah. So it's a sequence of linear maps. Uh, 0 to AK to BK to CK to 0. And such that for all k, this is a short exact sequence of vector spaces. Okay, so that's a short exact sequence of Cochain complexes. And now, because I and J are Cochain maps, it induces maps in cohomology, right? For all k. So for all k, you have these maps in cohomology, okay? But, you know, these sequences are not exact, right? Not necessarily exact. So, now, okay, so these maps are easy to define. But it turns out that there's a way to connect all of these sequences. So there's a map from here going to here for all k that we call D star. And so in this way, you can connect together all the rows into one sequence. And that's called the long exact sequence induced from a short exact sequence of Cochain complexes. And next time we're gonna, well, just, I think I won't prove it, but yeah. So this long, or next time we'll define this connecting homomorphism. And then the theorem is that the long exact sequence that you get is exact, okay? Okay, so we'll end it here today. I'll see you next time. Maybe I will have presents for you next time, you know? If not next time, next week, yeah. All right, so make sure that you sign the attendance sheet. And yeah, I'm happy to stay and chat with you, you know, if you have questions or if you just want to chat. Yeah. So my office hours will be after class, and also you can make appointment with me. Originally, I was gonna sit in my office from 2 to 3 to receive you, but nobody came anyway, so I don't think I'll do that, you know. So if you want to see me, just make an appointment with me, or you can talk to me after class, all right? Yeah, see you on Thursday.